Hey guys, welcome back to my channel. I'm Anay Gupta and I'm so glad to have you here today. For logic freaks like me who love math and physics, chemistry can smack the living daylights out of your soul. However, I found the secret sauce to conquering chemistry's horrors as I became the India topper for AS level chemistry in 2024. Additionally, I was also the India topper for AS level physics, world topper for AS level mathematics, and the All India rank 1 for my AS level exams. Today, I will enter the lion's den once again as I attempt to solve the exact May-June 2024 chemistry AS level practical paper that made me the India topper. Let's see if I have it in me to solve it once again or not. Whatever it is, guys, I am going to be making sure to send some very important tips in this very ambiguous paper. So I really hope that you make it to the end. And when you like this video, please make sure to comment down what was your favorite part, subscribe to my channel, and share it with as many people as possible. Let's get started. All right. So in our chemistry AS level practicals, we will generally be finding two different things. Either we will be finding the identity of a compound, or we will be trying to find how much of a compound is present in a particular sample. So there are two different experiments. First, we have quantitative analysis, and secondly, we will have qualitative analysis. Quantitative analysis generally consists of two of three questions: a titration experiment to find out the enthalpy change, or an experiment with a difference in mass methods where you heat a compound and then weigh the compound and then just calculate the difference in mass to calculate the identity of the compound. For us, the first experiment over here was a titration experiment. Let's read through the questions and then we can explain further. When ammonium compounds are heated with sodium hydroxide or calcium hydroxide, ammonia is liberated. The ionic equation for the reaction is NH4 plus OH minus gives NH3 plus H2O. Fa1 is prepared by heating 10 centimeter cube aqueous ammonium chloride, NH4Cl, with 25 centimeter cube of 2 mole per decimeter cube sodium hydroxide, NaOH. The sodium hydroxide is in excess. The reaction mixture is cooled and diluted to 250 centimeter cube with distilled water. You will determine the concentration of the aqueous solution of ammonium chloride by titrating the remaining sodium hydroxide from the preparation of Fa1 with a known concentration of sulfuric acid. Okay, now this entire big paragraph, I just read it for you, but we can start with the question. Okay, so method: fill the burette with Fa2. Okay, so you will be given a burette. You first rinse the burette with water, then you rinse the burette with Fa2. Okay, after you've rinsed it, you fill the burette with Fa2. Pipette 25 centimeter cube of Fa1 into a conical flask. So you know, using the measure, you just suck 25 centimeter cube of Fa1 until the mark on the pipette, and then you transfer it into your conical flask. Add a few drops of Fa3 to the conical flask. So your Fa3 is your bromophenol indicator, the acid base indicator, and perform a rough titration and record your burette readings in the space below. So now what a rough titration is actually supposed to mean is, you know, you just sort of run down the liquid very quickly and just swirl it, and then, you know, whenever you just see the liquid change color in the conical flask, you stop the tap and you take the reading of the rough titer. That is what it is supposed to mean. But how do we hack the system over here, guys? So you perform an actual titration. So in actual titration, you know, just take the titer drop by drop very gradually, and you stop the tap at the exact moment when the color in the liquid changes color. Okay, so I advise people to perform a proper titration. Okay, and then they can just sort of add, say, a 0.4 or 0.5 centimeter cube here and there to their rough titer. Okay, now one very important key point to note here is we have to record our values to accurate significant figures. Okay, so if you do not round your answers to the least count, you will lose marks. Just as our physics practical, you have to round your recorded values to your, you know, accuracy of the instrument. So we have been given a burette over here. the burette measures to the nearest 0.05 centimeter cube. Correct? So we have to record our answers to two decimal places. Okay, so I can say that my rough titer. Also, guys, since there is no way for me to actually perform the experiment, I will just be taking you through how to present your answers and how to, what is the exact methodology of performing the experiment. So I will try to convey that to you by explanation. And in most of these cases, you get answers for your procedure, for your presentation. Correct? So that is more than what's important, right? So you will 90% of the times get a fairly accurate reading, but how do you show that is what is important. And we will be discussing the calculations, which are the actual dreaded part for most of the students. Okay, now let's begin with a rough titer. So let's say that I remember that my actual reading was somewhere around 23.7 or 23.8. Okay, so let's say my rough titer is equivalent to 24.10 centimeter cube. Okay, now, carry out as many accurate titrations as you think necessary to obtain consistent results. Make sure any recorded results show the precision of your practical work. Record in a suitable form in the space below all your burette readings and the volume of FA2 added in each accurate titration. Okay, so firstly, guys, we need to record our values to two decimal places. That has been established. Now, we also need to repeat our experiment multiple times until we find a concordant reading. Now, what is a concordant reading? Concordant basically means that the two titration or the two titer values are within 0.1 centimeter cube of each other. Okay, so I generally advise people, and what I generally did myself was also did three experiments. Okay, and in those three experiments, I ensured that at least two of my readings were concordant. Okay, if for example I poorly performed an experiment, or let's say just I, just was a little late in closing the tap, and a little more of the Fa2 flew into the conical flask, then I would just simply not record the reading. You don't want to show an examiner that you have done the experiment 6 different times, but only 3 different times you have found a concordant value, and the remaining 3 other times, just have found random readings. So if you're getting random readings which you don't really think make logical sense, you might not as well just include them in the question answer, and you can just sort of repeat the experiment because you have ample of contents, ample of FA2 and FA1 supplied to you in the exam. Okay, so what table do we need to form? So first we will say initial burette reading. Okay, I can say experiment number or experiment initial burette reading. Okay, these headings are very crucial, and we give the unit. So our unit is centimeter cube. Okay, the next is our final burette reading. Again, our units are centimeter cube. Guys, units are very important. Forget the units, forget the marks. Titer and centimeter cube. So you need to have a table like this. You can just put it into a horizontal format, that's also fine, but I prefer a vertical format. Now I will have experiment number 1, 2, 3. Okay, now the initial burette reading can be anything on your scale. Okay, so I generally prefer to start around 0.10, because 0.00 it is not really easy to decipher from your eye. So 0.10 is a very nice and safe starting point. Now let's say my final burette reading is 23.90. So my titer will be 23.90 minus 0.10, which is going to be 23.80. Okay, now let's move forward. Now let's perform the experiment again. We say I can simply start at 23.90 here. That's also all right, not a problem, guys. And now let's just say that my next titer value is 40, like final burette reading is 47.75. So my titer comes to be 23.85. Okay, that's pretty all right. And then now I have to refill my titer, refill my burette again, because I cannot start from 47.75. You need to have that knowledge that the burette only holds 50 centimeter cube, right? So you refill the burette, and let's say I start again at 0.10. 23.10, and this time I stop at 23.85. So my titer is 23.75. Now all of these three readings are concordant because the range of the readings, like the difference between the highest reading and the lowest reading, is just 0.1 centimeter cube, correct? So they are concordant, they are all acceptable values. Okay, so very important, concordant readings, two decimal places, and this nice little table format that we have presented our results in. Now the rest of the marks are for accuracy. So your readings will be compared to your supervisor's readings, and if you have performed the experiment correctly, they should generally be right. Okay, from your accurate titration results, calculate a suitable mean value to use in your calculations. Show clearly how you obtain the mean value. Okay, so we simply say mean equals to, when we find the average over here of all our three titer values. So I say 23.80 plus 23.85 plus 23.75, right? Because these are our readings over here. Now if you have one value that is not concordant, okay, so instead of 23.85, let's say my reading was 23.95 or 24.00, then I would not include that reading in my mean. Okay, but as I told you, I will just advise you to not record that reading only. So record only concordant readings. That's my advice. So the average comes up to be 23.80 centimeter cube. Now this is just speculation. I think it was something around these lines, but as I told you, I don't really remember exactly. Okay. Now again, two decimal places. You need to record two your accurate number of significant figures. Now, this was recording, right? Like I just told you in the physics practical video. If you haven't watched it, go watch that here. But when you're recording a value, you need to record to the instrument's least count. But now when I'm calculating values, I will need to calculate to about 3 or 4 significant figures. Since my value recorded over here is correct to 3 or 4 significant figures, that's why I will have to calculate to 3 or 4 significant figures. All right, now we have come to the numericals. So calculate the amount in moles of sulfuric acid present in the volume of Fa2 in B. Now whenever we start with calculations, we first should just go back to the question, look at all the equations given to us. So these two equations will be very important in our calculations, and we should always just make sure what the burette was filled with. So what our titer is actually comprising of. So our burette was filled with Fa2. That means this titer value that we have got over here, this is of sulfuric acid. Okay, so the amount of sulfuric acid in Fa2. Now we will use the formula N is equal to C times V. N is the number of moles, C is the concentration, V is the volume. So N is equal to the concentration of sulfuric acid has been given as 0.0520, and the volume has been calculated over here. So 23.80. Now remember, this is centimeter cube and the volume is been given per unit decimeter cube. So we will divide this by 1000 to convert centimeter cubes to decimeter cube. And if you just put this into our calculator, we get that as 1.2376 into 10 raised to minus 3. Now, I just need to round it to an appropriate number of significant figures. So I can give it to 3 significant figures, or I can give it to 4 significant figures. Okay, so I'll just give it to 3 significant figures. So 1.2376 into 10 raised to minus 3, which is approximated to 1.24 into 10 raised to minus 3 mole. Okay, so 1.24 into 10 raised to minus 3. Now, use your answer to C2 to calculate the amount in moles of sodium hydroxide in 25 centimeter cube of Fa1. So now they want to calculate the moles of sodium hydroxide. How do you do that? You use this equation over here. Okay, so we know that if there is 1 mole of H2SO4, there are twice as many moles of sodium hydroxide. So I can simply multiply the moles of sulfuric acid by 2. So 12376. I don't want to premature round my answers, and I double the value. Okay, so I get that as 2.475 2 into 10 raised to minus 3. So I can round that off to 2.48 into 10 raised to minus 3 mole. So 2.48 into 10 raised to minus 3 is your answer. Next question. Use your answer to C3 and the information given to calculate the amount in moles of sodium hydroxide that reacted with the ammonium chloride when Fa1 was prepared. So we have been asked to find out how many moles are reacting in this of NaOH are reacting with the NH4 plus. Okay, so initially we have, let's say, X amount of moles. So we have been given some calculations over here, some figures over here. Some of the OH minus ions will react with the ammonium ions, the NH4 plus ions, and the remaining ions will react with our H2SO4 or the hydrogen ions. Okay, so we need to find out how many reacted first before we could add Fa2. So first I will say initial moles of NaOH. Okay, so my initial moles of NaOH will be given by N equals to C into V. So 25 centimeter cube of 2 mole per decimeter cube. Okay, so that gets us 2 into 25 upon 1000. So 2 into 25 by 1000 gets us 0.0500 mole. Okay, this was how much we had initially. Now the amount of moles of sodium hydroxide that have reacted with Fa1 is 2.48 into 10 raised to minus 3. This mistake is another mistake I see a lot of people making, is they don't read the question fully. Okay, so the reaction mixture is diluted to 250 centimeter cube. Okay, but so there is initially 250 centimeter cube, but the titration is happening with only 25 centimeter cube of Fa1. Okay, the titration is happening only with 25 centimeter cube of Fa1. So I will say that the amount of NaOH in 25 centimeter cube of Fa1 is going to be 0.0500, right, divided by 10 minus okay. Okay, so there was 0.05 moles of NaOH initially. Okay, so that means that if I took all of the 250 centimeter cube of Fa1 in my titration, the amount of NaOH or the amount of H2SO4 that would have reacted would be 10 times more, right? Amount of NaOH that would have reacted would be H2SO4 that would have been reacted was 10 times more. So I will say that final moles of NaOH in Fa1 would be 2.48 into 10 raised to minus 3 into 10, right? 250 upon 25, because out of 250 centimeter cube, we only took 25 centimeter cube. If we have taken the full 250 centimeter cube, it will be 10 times larger. So that becomes 2.48 into 10 raised to minus 2. Okay, so that means that moles or amount of NaOH reacting with NH4 plus or NH4Cl is going to be 0.05 minus 0.024. And I can just sort of expand this into a decimal form. And if I put this into my calculator, I get that as 0.0252 mole. That's my answer. This is your entire answer. Use your answer to C4 and the information given to calculate the concentration in mole per decimeter cube of the ammonium chloride solution used to prepare Fa1. All right, guys. Another very simple question. So we know that 0.0252 moles of NaOH has reacted with NH4Cl. Now, what other information have we been given? That 10 centimeter cube of ammonium chloride was used in the initial equation. So we will simply use our equation n equals c into v. So that means c is going to equal n upon v. Okay, now n has been given as 0. Now we have to just check this stoichiometric equation. The equation is 1 is to 1, right? For every one ion of ammonium there is one hydroxide ion. So that means the same amount of moles of NH4Cl have reacted, that is 0.0252. Okay, so our n is 0.0252. Now our volume has been given to us, that was 10 centimeter cube. So 10 centimeter cube, if I just convert that into decimeter cube, that would become 0.010, right? Now if I put this equation on my calculator, I get that as 2.52 mole per dm cube. That is your answer. Okay, when ammonia gas is prepared by heating one of its salts with calcium hydroxide, it can be dried by passing it through a drying agent. Drying agents for gases include calcium oxide, calcium sulfate, concentrated sulfuric acid, and phosphorus oxide. Select one of these drying agents and suggest why it is not suitable for drying ammonia gas. Now, this is just trying to test whether you can think on the spot. You might just know all the formulae, you have used all the formulae, but let's see if you can make a good critical thinker. So if you notice what differences can we take out of these solvents or solutes. If you Okay, now we just have to sort of find the difference between these compounds. So if we notice, these compounds are basic, and these two compounds are acidic, right? Now we know that ammonia is a basic gas. So if we use an acidic drying agent, then there will be a neutralization reaction. There will be an acid base reaction which will just neutralize the ammonia gas. So the ammonia will react. So one of these reagents, I can safely select concentrated sulfuric acid, because I will say that H2SO4 is acidic, hence it will neutralize or react in an acid base way basic ammonia gas, right? This is your critical thinking that you have to apply in this question. Next question. A sample of ammonium bromide has been accidentally mixed with another salt. A student suggests that the percentage purity of the ammonium bromide can be determined by measuring the change in temperature when a solution is prepared. The enthalpy change when the sample dissolves in water, delta H, can then be calculated and compared with the literature value for ammonium bromide. You will carry out the student's experiment. Fa4 is ammonium bromide, NH4Br, with mixed with another salt. So first, we do not really have to pay so much attention to this entire contextual paragraph. We can first just carry out the method. Okay, support the cup in a 250 centimeter cube beaker. So you will be given a polystyrene cup. Okay, in that cup, you put the cup in the beaker. Use the 25 centimeter cube measuring cylinder to transfer 25 centimeter cube of distilled water into the cup. Place the thermometer in the water and tilt the cup if necessary, so that the bulb of the thermometer is fully covered. Recall the temperature of the water in space for results. So what do we do is basically you take a measuring cylinder, okay, and you, using the bottle of distilled water, you add 25 centimeter cube of distilled water into the measuring cylinder. Okay, so there's the measuring cylinder. I add 25 centimeter cube of water until I reach the 25 centimeter cube mark. Now I transfer all of the water into my polystyrene cup. So I have a beaker here, and in the beaker, I will support my polystyrene cup. Now I have 25 centimeter cube water here. I will add a thermometer and I will measure the initial temperature of the water. Okay, record the temperature of the water in the space for results. Weigh the container with Fa4. So now here, what do we want to do? We just want to record every reading that we are taking. So first reading that we have taken is initial temperature of water. Now I can add units like this, degree Celsius over here, or I can include my units in the temperature I record. So let's say my answer is 25 degrees Celsius. Now whatever thermometer you have been given to, record your values to that particular least count. So if your thermometer is accurate to say 1 degree Celsius, then you have to leave it as a whole number. If it is accurate to your 0.5 degrees Celsius, then you have to record it to 1 decimal place. Okay, now let's say that my thermometer was accurate to 1 degree Celsius. Weigh the container with Fa4. Record the mass. Okay, so now I have a container, a separate container that was provided to me, and in that there was some Fa4 solid. Okay, so I say mass of container plus Fa4. So let's say that that is 5 gram. Okay, just a hypothetical example. So 5.00 grams, again to the least count of the weighing scale. Then add all of Fa4 to water in that cup. So I transfer my Fa4 here, stir the mixture gently so that the Fa4 dissolves, measure and record the minimum temperature reached. So what do? You keep track of the thermometer temperature until it is falling. Okay, so you see when it is falling, in the moment that you see, okay, now it is not falling anymore, it is just plateaued, it is still, and then after a moment or two it starts rising, you record that little temperature. So like every 5 seconds you keep taking readings in your head, and then the lowest reading that you get, you record that particular reading. So let's say that I write minimum temperature of solution. Now I don't say minimum temperature of water, but rather solution. These small things can cost you marks in moderation. Okay, so let's say that this was say 17 degrees Celsius, just hypothetically. Okay, now I calculate and record the change of temperature. So what is my change in temperature? The change in temperature is always final minus initial, right? So 17 minus 25. So change in temperature is negative 8 degrees Celsius. It is reduced by 8 degrees. Okay, now weigh the container with any residual Fa4. So mass of container plus residual Fa4. So let's say that that is 2 gram. Okay, so the mass of Fa4 added to the cup, a mass of Fa4 used, is going to be 3 gram. Right, now these are just very hypothetical readings, but you need to record your values like this for your second question. Okay, now before we begin the calculation part of the question, I always suggest we just take a look at the paragraph above and see if we have been given any condition, any specification, any value that we have, missed, so that we don't make an error in the later stages of the question. Like, if we did not read the question properly, we would have definitely missed the 250 and 25 centimeter cube part of the question, right? So let's just sort of take a quick read. Or you can pause the video and read, but as of now, there has been no condition specified in this question. So calculate the energy change in joules for the reaction. So all our readings that we need are recorded by us ourselves. So the energy change, we know that the formula for energy change is the formula of specific heat capacity, right? So we say mc delta T. So m, or the mass that we need to use over here, is the mass of water, right? Because that is the temperature of water is changing, of the solvent is changing. So we are adding 25 centimeter cube of water, and we know that the density of water in gram per centimeter cube is 1. So our mass in grams is going to be 25. Okay, now my specific heat capacity in grams, not in kilograms, guys, grams per Kelvin per kilo. My specific heat capacity in joules per Kelvin per gram, okay, not per kilogram, is 4.18 for water. You need to know this. And your temperature change is negative 8. right? -8. So if you put it into a calculator, you get that as -836 joules. That is your temperature change, minus 836 joules. When 1 mole of ammonium bromide dissolves in water, the enthalpy change delta H is 16.8 kilojoules per mole. Use this value to calculate the amount of ammonium bromide in the 25 centimeter cube of solution Fa4 used in your experiment. Okay, so they are just asking us moles of ammonium bromide. Okay, so we have the delta H, the enthalpy change, and we have the energy change in joules. So we can say that the amount, or N in H4 Br is going to be joules upon kilojoules per mole, right? So I say -836. I can just take that a positive value here. 836 upon, this is kilojoules. So I need to convert this into joules. So I say 16.8 times 1000. Okay. So here 836 upon 16.8 into 1000, that gives me 0.0498 moles. Correct to three significant figures. 0.0498. Next question, calculate the mass in grams of ammonium bromide in your sample. So here we need to understand that firstly we need to calculate the MR of ammonium bromide. Okay, let's go on to our periodic table sorry, and find the MR of NH4Br. So N, or nitrogen's relative atomic mass, is 14 plus 4 for 4 hydrogens, and bromine has a relative atomic mass of 79.9. So that gives us 97.9. Okay, so MR is 97.9. Okay, that is our MR. Now calculate the mass. So from moles we need to find the mass, right? So what is our formula? So mass is going to equal MR times the number of moles, correct? So that equals 97.9. We already have the moles of NH4Br over here, which is 0.0498. That gives us 4.86 grams. Hence, calculate the percentage by mass of ammonium bromide in your sample. So percentage by mass is now equal to, we have 4.86 grams of ammonia bromide, so 4.86 upon the total mass of Fa4, which is 3 grams. Okay, obviously that is not really possible, but since I did not have realistic readings, I just put random readings down. So let's say 3.00 into 100, right? So that will give you 162.5%, which is obviously wrong, but then you will get some value that is where a numerator is smaller than your denominator, and you will get a percentage less than 100, okay, over here. But this is how the entire calculation is supposed to be carried out. So I had 162.5%, which is almost suicide in this condition, but okay. Next question. Another student states that this method is not accurate as the enthalpy change when the other salt dissolves in water could be exothermic. Suggest how the calculated value in B4 would change if the other salt dissolves in water exothermically. So if the other salt is dissolving exothermically, it is actually releasing heat energy. So what happens is, when I'm performing the experiment, the temperature change is going to be smaller, right? The temperature decrease will be smaller. So if I have a smaller temperature decrease, then all of my calculated values here, my energy change and my moles or amount of NH4Br will be smaller. So my energy change and amount of NH4Br will be smaller. Hence, mass of NH4Br will also be smaller. Right? We are just going logically in the order that they have provided us. So mass of NH4Br will be smaller. So percentage by mass will be smaller. Now, always remember that if your value that you are using is in the numerator, so for example, my delta T value will decrease. That is what I've established. Now, in energy change, it is in the numerator. So if delta T reduces, energy change, the value of energy change reduces. Over here, this value that I've calculated with delta T, 836, is in the numerator. So if energy change reduces, this also reduces. Now again, this amount that I've calculated is in the numerator. So if this reduces, right? And again, the final time, the mass of NH4Br is again in the numerator in the final equation. So if the mass of NH4Br reduces, the percentage by mass also reduces. If anything was in the denominator, then if the, one thing reduces, the other thing increases. Okay. So always be careful of your relationships like that. The maximum uncertainty in a single thermometer reading is plus minus 0.5 degrees Celsius. Calculate the maximum percentage error in your temperature change recorded in A. Now, in a single thermometer reading is 0.5 degrees Celsius. But if you see, we have taken two temperature readings, the initial reading and the minimum reading, right? So the total uncertainty over here, total uncertainty is 2 times 0.5 because I have taken two readings. So that gives us 1 degree Celsius. So your percentage uncertainty, a maximum percentage uncertainty, whatever, is 1 over a temperature change. So your temperature change is 8. That gives you 12.5%. This is your answer. Okay, 1.8 into 100, obviously, sorry. 1.8 into 100, which gives you 12.5%. Okay, now, next question, qualitative analysis. For each test, you should record all your observation in the spaces provided. Example of observations include, this is very important, color changes seen, the formation of any precipitate and its solubility in an excess of the reagent added, the formation of any gas, and its identification by a suitable test. You should record clearly at what stage in a test an observation is made. When no change is made, you should write no change. When reagents are selected for use in a test, the name of or correct formula of the element or compound must be given. If any solution is warmed, a boiling tube must be used. If a solid is heated, a hard glass test tube must be used. Rinse and reuse test tubes and boiling tubes where possible. No additional tests should be attempted. Okay, now since I do not have the equipments over here, I don't have the solids and compounds with me, I cannot really attempt this test at my home right now, so I can't help you with this question. But I suggest you go through the mark scheme. The mark scheme will show you how to record your answers. Okay, one thing I will always tell you is whenever you find something like a carbonate ion, or say an oxygen gas being released, there's a possibility of that. Always test for gases. Testing for gases is so underrated yet so important. Okay, so just do that, and you always have your reactions and your tests and everything given to you. So all your tests that you may need to do, all your results and how they relate to the cations and anions have been given to you. So your cheat sheet or your notes is in your question paper. I mean, what more do you want, guys? So you just need to just match what you see with what is written in these tests here. Now another thing is, sometimes like what happened with me was I could see multiple color changes. Okay, so say first I think I saw yellow, and then it sort of transitioned to off white with time. Another time it was, I think, bluish green or something, and then it became brownish with time. So whenever something like that happens, you need to specify both the colors and the order in which that happened. Okay, always specify your precipitates, if they are forming, the color of the precipitate, and if they are dissolving or if they are not dissolving. Okay, that is another very important thing. And if you don't see anything, just state the color of the solution. Like if just the solution is become turning from, say, colorless to blue, then tell the color change. Okay, even that is very important. If you see something like condensation, okay, that is also sometimes a point, or effervescence, just bubbling or fizzing. So whatever you see, however small it might be, please write that. Don't only think that, okay, I just need to write about the color change and I will score my marks. No, every little thing counts. If you see a flame, okay, if you're heating a metal and if you see the flame turns color, write about the flame test. Okay, whatever you see, please write that in your answer. Okay, we also had organic tests to be carried out over here. So over here, please, learn your organic tests. You will have tests for aldehydes and ketones. You will have your 2,4-DNPH test. You will have your, silver nitrate tests. So all of those tests, that are specified in your chapters of halogenoalkanes, your carboxylic acids, and your aldehydes and ketones. Please learn those tests before your exams. If it comes, it is going to be free marks for all of you. Okay, so I am sure you are going to ace it. Learn all your organic tests, be it the KMNO4 test, your K2CR207 test. Learn your procedures, learn your formulae, and just don't get confused. Just follow step by step. Apply all your formulae, your stoichiometric equations, and I am sure this is an easy 40 marks for the taking. I was scared of it too, but with just some practice, I could score an India topping performance. So if I can, I'm sure you can too. All the best, guys. Please don't be, intimidated by the chemistry exam. And if you've just taken a much more difficult physics exam already, I'm sure you will ace this pretty easily. All the best. If you like this video, please make sure to comment down below what you like. If you have any questions, put them down below. I'll get to you as soon as I can. Everything else we will be taking care of next time with much more. Next time I will come up with more walkthroughs for more papers and more subjects. If there's anything specific you want, please let me know down in the comments below. If you like this video, give you a like, subscribe to my channel, and share it with as many people possible. Thank you so much. All the best. I'll see you soon next time. Bye.
चल उठ जा, let's crack it, जोर दे लगा, let's crack it, भीड़ को छोड़ दे.